For this first problem in Review Quiz Chapter 9, we have population proportion, and we have a given level of confidence. We're just trying to figure out what is the interval level. Now, of course, you could go in the textbook, open it up, and find the formula for it. Once it loads here. We get our point parameter by doing x divided by n. Level of confidence 1 minus alpha times 100%. And you can see how we kind of find the ranges, the lower bound and the upper bound. And right here is the formula. So you're taking p hat times 1 minus p hat over n, square root of that, and then you have to find z alpha over 2. That's based on your confidence interval and using the table of values. Of course, you don't need to do that. What you can just do is open StatCrunch. And this is a population proportion, which is the same thing as saying proportion stats. We only have one sample here. And then we have the summary. Data is like actual data points that tell you test 1 was a success, test 2 was a success, test 3 was a failure, so on and so forth. What we have is a summary. We have x equal to 540, n equal to 1200, and a confidence level. So the number of successes is 540. The number of observations is 1200. We will talk about hypothesis tests in a later chapter. For now, we're talking about confidence intervals. We want a 95% confidence interval. That's what we have here. So we can compute. And these are the stats we get. Lower bound and upper limit. Lower limit and upper limit are shown. We need 3 places, so 0.422. Okay. And upper limit is 0.478. Let's check that. And that's correct. So let's move along. National survey of 1,000 adults. Okay, so we have 1,000. 15% dreaded Valentine's Day. Margin of error was 8.1 percentage points with 9% confidence. So explain what this means. So first off, we can already get rid of some stuff. Confidence is not a range of values. We are 90% confident. So 90% confident that's 15%. In 90% of samples, no, that's not true. So it's going to be either B or D. The 90% confidence is how confident we are we have the actual value. And we do not include just a single number. Because of the margin of error, we include a range of numbers. So we're 90% confident that it's within this range of numbers. That's the idea here. This is always how it's going to look like, is 90%, 95%, 98% confident between a range of numbers. You should always expect that. That's correct. Okay, we have 251 of 1,000 adults, 19 years or older, confessed to, I don't know what they said confessed to, bringing and using their cell phone every trip to the bathroom. That seems like a low number for that, but let's just go with it. What is the sample in the study? The population of interest. So determine the sample in this study and select the correct choice below. So the sample is all adults 19 years age or older. No, it's not all adults. That'd be way, way, way more than 1,000 adults 19 age. So it's going to be the sample is 1,000 adults 19 years of age or older. Okay, determine the population of interest. Well, that would be all adults 19 years of age or older. Since we have a sample of that, that's going to be the population of interest. Okay, what is the variable of interest in this study? Is it qualitative or quantitative? The variable of interest is if they're going to bring the cell phone or not, right? 251 did bring them, so that's the variable of interest. Not the adults, not the age. We don't care about the age at all. It's not the variable here. The 251, which is successes, is bringing the cell phone or not. That's what the variable of interest is. The variable is qualitative with two outcomes, or quantitative. Definitely qualitative. Either they do or they don't. So yes or no, pretty much. Numerical measures of individuals are provided. No, they're based on a characteristic. So either they do or don't bring it. So it's yes or no, right? That's the idea there. Okay, based on the results, what is this should be point estimate. That's just going to be 251 over 1,000. 0.251, of course. I didn't need to use a calculator for that, but I did. Okay, explain why the point estimate found in part C is a statistic. Explain why it is a random variable, and what is the source of variability. Okay, so why is it a statistic? So we have value may change depending on the individuals in the survey. So explain why the point estimate found is a statistic. This will change, but that's not what we're talking about. We're talking about statistic, I believe. So using make inferences based on the sample. I believe it's a statistic because it's based on a sample. It'd be a parameter if it was based on the population. Based on the survey, it doesn't matter, and large doesn't matter. So why is a point estimate found in part C a random variable? So random variable means that it can change. And that tells you, well, it can change depending on the individuals in the survey, right? If we had a different survey of 1,000 adults, we should have a different number here, typically. Okay, what is the source of variability? That'd be the individuals selected, of course. Not the question asked, that's always the same. The sample size, you could kind of estimate that if you had more sample size, you could still kind of the proportion would still be the same. And random errors, that shouldn't be a part of the survey. It's really about the individuals. Okay, construct and interpret a 95% confidence interval. Okay, so this we can use StatCrunch for. We have a proportion, so we can do proportion stats. We do have the data, or no, sorry, the summary. The successes is 251, observations is 1,000, confidence interval of 95%. Do that. And we have our numbers right there. So our, which one we're going to choose, there's not a 90% probability. We are 95% confident. It's not a probability. Confidence interval is a confidence level of your answer. 95% confident. That is between, go back to StatCrunch here, make it just a little bit smaller. Let me see if I can rearrange this a little bit. All right, is between the lower bound is, let's see, once 3 places. So we have 0.224 and 0.278. Okay, what ensures that the results of the study are representative of all adults 19 years of age or older? That would be because of random sampling. It has to be through that, else it would be pointless to specify 19 years of age or older. Large sample size doesn't guarantee it. You could get a large sample size of all the same people if you just choose wisely. High confidence level, if you had a higher one, you get like everyone in there, but random sampling is what you're looking for there. Let's check it, and it's all correct. Okay, moving on to the next one. 37% of people polled answered yes to, are you in favor of the death penalty? The margin error was 2%, 96% confidence. So the minimum number of people surveyed was, and this one, I believe we're going to have to use the formula. We're looking for the number of people surveyed. And you should see one at the end. Let me find it here. Okay, on the second to last page, we have the formulas here for sample size needed for estimating a certain population proportion. And it gives you everything you need right here for that. So let's take a look again at what we're looking at. Okay, we got 37% of people. That is, let's see, is the population, is p hat. 2% was the margin of error. That's going to be E with a 96% confidence. So that's going to be the Z. If a prior estimate of P is unavailable, sample size. So we do have P. So we're going to use the top equation here. Okay, let's try this out. We have p hat, which is going to be 0.37 times 1 minus p hat. It's going to be, you go up 3 and 60, 0.63. And this is multiplying z alpha over 2 divided by e. Now the margin of error was 2%, so 0.02. The divisor, and then we have 96% confidence, which means alpha is 4, right? 1 minus, I guess, maybe 0.04, I guess. Okay, and we need to find that on the table, 0.04. Of course, that's alpha over 2, so it's going to be 0.02. So we want 0.02 for the area. It looks like it's between these two numbers, 0.02. And that is negative, or just, you can just use a positive, 2.0, 2.0, 2.055, I guess. What you could use, 2.055. Let's try it out. Let's see what they say. Okay, so 2.055 divided by E was given to us as 0.02. And then you square that, giving us, we're going to round up. So it's going to be 2461. 2461. Check that. Not correct. Let me see what I did wrong here. All right, so what I got when I calculated it was 2461. Now this isn't the correct answer because it's actually 3 off. That's because I used the table. And the table inherently has an issue with, you can't be very accurate. To solve it, what you can do is you can go to StatCrunch and proportion stats, one sample. So what we have. And we're going to go here to power sample size. Sorry, that's not what I wanted to do. I want to do width sample size. And you can use this calculator to do the work for you. So we have a confidence level of 96%. The target proportion is going to be the 37% of people, so 37. The width, now the width in this case is actually the width of the full interval. The margin of error is just how much it is plus or minus on around the target proportion. So you add it together and you get 0.04. So that's what the width is, 0.04. And of course the sample size is the only thing we don't know. So compute that. And you see we get 2458. So 2458. Check that. And it's correct. So if you can help it, don't use the tables. It's just, they don't like to have very much. You could probably get 2459. It'd probably be fine too, but try and use a calculator whenever possible because it'll be more accurate. Okay, so this one is now the change between proportion, which we were just doing, to random samples with sample means and standard deviation. So now we're looking at the t distribution instead of the z distribution in which we were looking at. Okay, So construct a 95% confidence interval. Well, StatCrunch. Now we want stat t-stats because of the setup that we're having. And we have the summary of the data. So we have the sample mean is 18.1. Standard deviation is 4.1. The sample size is 34. Again, we'll talk about the hypothesis test later on. Confidence interval is what we're dealing with. Oh, 95%. That's perfect. Compute that. Oops. 2 decimal places, so 16.67. And 19.53. Okay, now it says do the same thing, but for a sample size of 51. So options edit, that'll allow you to change the data you plug in and then compute. So same stuff, just the sample size is different. 16.95 and 19.25. Okay, so what we did here is all we did was increase the sample size, and that increased the lower bound, decreased the upper bound. In other words, it shrunk the interval, interval of values. So the margin of error, that's what I was trying to say. The margin of error decreased there, became a smaller interval. Okay, now for this one, from the first one is n equal to 34 and 95% confidence level. Here we have a 99% confidence level for n equal to 34. So let's go back to StatCrunch, change that to 34, and then change the confidence interval to 99. Oops, 99. And now we have a lower limit, 1618. Upper limit of 20.02. Okay. And as you can see, we went from 1667 to a lower, 1953 to higher. So it actually increased the error margin. The margin of error increased there, which makes sense because if you're more confident with your answer, that means you're taking up more space, or you're allowing for more solutions. So you get a bigger interval that your solution could contain. Of course, if you look for 100% confident, then that'd be everything, right? So that wouldn't be very helpful. That's the reason why you always see 99%, 95% confidence, that kind of stuff. So if the sample size is 15, what conditions must be true? First off, sample size 15, that's less than the 30. Therefore, we don't have the assumption that it's standard normal or just normal distribution. So the only way this could be a normal distribution is if not sample size must be large, the sample size is 15, so that can't be it. That must come from a population that's normal distributed and sample size must be large. That's not the case. Our sample size is small. All you need is a normal distribution sample, and no matter what sample size you have, it should be approximately normal. Let's check those, and they're correct. Okay, moving on. Okay, survey of 1,100 adults, asked how many hours they worked in the previous week. 95% confidence means lower bound is 42.7, upper is 44.5. Okay, provide 2 recommendations for decreasing the margin of error. All right, if we want to decrease the margin of error, one thing we can do is decrease the confidence level. 90% confident would allow you to have a smaller confidence level interval. We just actually looked at that. If you increase the confidence interval, you increase the margin of error. So if you want to decrease the margin of error, you decrease the confidence level. Use fewer degrees of freedom. Let's see if I can actually show that. Let me pull up the t-table real quick. Okay, here are the formulas for finding the lower and the upper bound for the confidence level. You see we have t times s over square root of n. S and n are going to come to play in just a minute, but t, see that if t is multiplying this thing, which means if t increases, the lower bound will increase, or sorry, the lower bound will decrease because it's being subtracted. And if t decreases, the lower bound will increase. So larger t, just like over here, if we had larger t here, we're adding onto it, so the upper bound will increase. Larger t, the lower bound will decrease. Larger t will make the interval larger, and a smaller t will make the interval smaller. So how does degrees of freedom affect t? And if you go to the t table, this is just a portion of it, but it'll show it just fine. Let's look down at the very bottom here, where the red column is. 1337 is for 16 degrees of freedom at 0.10. And if you increase the degrees of freedom, you see that we get larger and larger numbers. In fact, if you have 1 degree of freedom, you have the largest of them all. And that's true for every single column. If you look up as you're going up, the numbers get bigger. So by decreasing the degrees of freedom, t increases, and if t increases, your interval gets wider. It gets more. The lower bound gets smaller, lower bound gets bigger. Okay, so the question was, we want to decrease the margin of error, not increase. So using fewer degrees of freedom will increase t, which will increase the size of the margin of error. So we do not want to use fewer. We want actually more degrees of freedom. In other words, a bigger population or bigger sample size. Okay, increase the confidence level. That's the opposite of decrease, so no. Decrease the standard deviation of hours worked. Well, going back to this thing, we can see the interval, the formula here. Standard deviation, what effect does it have? It actually, because it's in the numerator here, just like t is, it's going to have the same impact as t does. So an increase of s, the sample error, or the standard error for the sample, increase of s is going to make the interval wider. Decrease of s is going to make it smaller. So decrease the standard deviation of hours worked. Is that what I just said there? I think standard deviation of hours worked. Oh, wait a second. It said standard. It didn't say standard mean. That's where I'm getting confused. So S is the standard error of the mean. This is the standard deviation of hours worked. You can't change the standard error deviation of hours worked because that's a population statistic. That's a constant. So this can't be done. So decrease or increase sample size. So let's go back to the population, or sorry, the equation here, or the formula. So n is in the denominator, which means if we increase n, that means you're dividing by a bigger and bigger number, which makes the whole thing smaller. So this whole thing will become smaller as you increase n. That'll make the lower bound less and less, or in other words, it gets tighter to the number. If you decrease n, you're decreasing by a smaller number, therefore the whole thing gets bigger, and the lower bound gets reduced, so the whole thing becomes a wider interval. I would test some numbers out. If it doesn't make sense, test some numbers out for both the upper and lower bound. The upper bound gets bigger when n gets smaller when n gets bigger. It just does the inverse operation. So if we wanted to decrease the interval, we must increase n. And hopefully that makes sense from a standpoint of like actually testing and having better data. If you have bigger sample sizes, your peak of the standard normal curve will be tighter because you'll be much closer to the actual population proportion or the actual mean. So it should make sense that if you increase the sample size, your margin of errors are going to get smaller because it all becomes much tighter onto the mean. Decreasing it makes it a much flatter standard normal curve, or I should say normal curve, not standard normal. Okay, check that, and we got it all correct. Okay, blood alcohol concentration of drivers involved in fatal accidents. Randomly selects 82 in 2009, and they have a sample mean of 0.16 with a standard deviation of 0.06. Okay, so a histogram shows that it's skewed right, highly skewed right. Explain why a large sample size is needed to construct an interval with that. Okay, so it's not normally distributed, first off. B and C can't be correct. It's skewed right. The sample size must be large to ensure that the sample mean will be approximately normally distributed. The sample size must be large to be greater than 5% of the population. Or sorry, not greater than that's why that one's not true. It should be less than 5% of the population to be normally distributed, but we must have a large sample size, over 30, to make it approximately normal. Okay, recently there are 25,000 fatal crashes, a positive BAC. Explain why this, along with the fact, using simple random sample, satisfies the requirement. Okay, so the sample size is likely less than 5% of the population. Also, it's a simple random, so we have that, and then we also know that it's above 30, so we can use the confidence interval for this because it's a normal distribution, so likely less than 5% of the population. Determine and interpret a 90% confidence level. Okay, so this is going to be a t distribution. We have the summary. The mean is 0.16. Standard deviation is 0.060. The sample size was, I believe, 82 such drivers, yes. We had a confidence interval of 90%. Okay, let us compute that. And now it says determinant, so we want the researcher is 90% confident. The BAC is not in the confidence interval. That doesn't make sense. 9% confident that it is in the confidence interval. 10% confident that it is in the interval. 10% confident that is in the interval is the same thing as the 90% confident that it's not in the interval. So those two are incorrect. So B is what we're going to be having as our solution for the choice there. And then now we need 3 places, 0.149 lower bound, and upper bound is 171. Okay. All areas of the country use 0.1 as the legal intoxication limit. Is it possible that the BAC of all drivers involved who are found to have positive BAC values is less than the legal intoxication level? So our mean was 0.16 and the standard deviation is 0.060. So is it possible that actually all the ones that we found are less than 0.110, which is much smaller than 0.16? It's actually, one standard deviation smaller. Is it possible? And the answer is yes. I mean, any value is possible for statistics. That's the reason why there's a confidence interval. And if you were to say you're 100% confident, that means you include every single possible value, but that doesn't tell you anything. So you can never be 100% confident that you have the thing. Just like a probability, if you're talking probabilities, you can really only be 1 or 0 probability. if there's no other possibility it could be. Like, for instance, if you flip a coin and you got a heads, the probability that it's heads is 1. But if you're about to flip a coin, the probability is not 100% heads or 0% heads. It's going to be 50%. You can't have a it's the same idea for both. Hopefully that makes sense. Yes, it is possible, but it is possible because it is possible that a true mean has not captured the confidence interval, but it is not likely. This is one standard deviation smaller, and it's only on that one tail, so it's highly unlikely that we don't contain it. This one is incorrect because it says it's possible that the true mean is not captured in the confidence interval, and it's highly probable. That's not correct because our sample mean is so much higher, and the standard deviation is, you know, not very much. It's just 0.06. That's not likely. So that should be what you should select. It's all correct. All right, we have pH of rain, 12 samples, and normal probability plot suggests that data could come from a population that is normally distributed. So we can use everything we have been using because we're assuming that the population is normally distributed, and we only have a sample size of 12, so we have to have that in order to use confidence intervals or anything. We're assuming it's normally distributed. Okay, so a point estimate. Really, all we're going to do is we're going to copy this to a table in StatCrunch. This is going to be a sample, right? Because it's not a proportion, it's a sample. So we're going to use a t distribution. And here we do have the data. We don't have a summary, we just have the data. We select the column that's in. We're not performing a hypothesis. We're going to use a 95% confidence interval, so that's what we want. The rest of this should just be fine. So, all right. The sample mean is the point estimate. We have 5.01. And we know it's going to be this one, not probability, confidence, not repeated samples. It's 95% confident. That's between what and what. We have 2 decimal places, so 4.73 and 5.29. Okay, that's our confidence interval for 95%. For 99%, we can do the same thing again, except now change this to 99. But yeah, if we're more confident, our interval should be larger, which you can see here. The lower bound went down and the upper bound went up. So we have a larger interval. 99% confident, 4.61 is the lower bound, 4.61, and 5.40 is the upper bound. What happens to that interval of confidence? So as the width, as the level of confidence increases, the width increases. This makes sense since the margin of error increases as well. So you just get more margin of error the more confident you are in your answer. Let's check it. It's all correct. Okay, this is the last problem. We have if ever married, how old when you were first married? And this is the information we get. We see we have the sample size, the mean, the standard deviation. This is, I believe, the sample error and the confidence level. So it's all given to us there. Okay, so the point estimate is going to be the mean, 720. This should be the error. I'm just going to check to make sure that's what SE means. I'm pretty sure it means standard error. But we'll just show that by taking the upper limit, 23.776, and subtracting that from the mean, 23.720. 0.56 if we half that. Okay, that I think that's the reason why it's coming from something there, but all you really need to do is just take the upper limit and then subtract from the mean. That gives you your error, which was 0.056. You have a 95% confidence, so one can be 95% confident. It's not a single value, it is a range of values. So one can be 95% confident that they're first married in those. All right, verify the results by computing a 95% confidence level with the information provided. So begin with the lower bound. You always start with the mean. You can actually write that in the next one as well. And then for the lower bound, we're going to subtract. Upper bound, we're going to add. And now we need to figure out what is the z, or sorry, t score, because we're looking at t values. And t value is going to be alpha over 2, so it's going to be 5 divided by 2 is 2.5, 2.50. Oh yes, of course. First off, we need to find the degrees of freedom, which if you look in your textbook, it's going to be n minus 1, n being the sample size. Here we have 26,570 minus 1 is 26,569, but this one doesn't have that on there. What it does have is like a z for like a very, very large sample size, which is what we have. So all we really need to do is use this final column, or sorry, final row, and find the column that we're looking at. We're looking at what was it, 0.25? Just forgot it. 95% confidence, so yeah, it's going to be half of the difference, so it should be 0.025. So that should make our z-score 1.960. Zero, and I don't think we need a 0, but 1.960. I do believe that is going to be n. Yeah, standard deviation. So n is going to be 26570. 26570. And now we just need to calculate that. 23.720 minus 1.960 times 4.665 divided by 26570 square root. And we get to 23.664. And you look up here, we have 23.664 being the lower bound. So that's all correct there. This one, we do the same thing. 23.72 plus times divided by root equals 23776. That's what we have up top. And there we go. All right, why is the margin of error for this confidence interval so small? And that should be clear because the divisor, which is n, is extremely large. The sample size used is very large. And that's all correct.